Good morning, everyone. This is Sitaram Maity from Saha Institute of Nuclear Physics, Kolkata. Today, I will discuss about the Hall coefficient, how Hall coefficient changes with the temperature and the applied magnetic field in a given semiconductor we have used. Then, why should we study the temperature dependence of Hall coefficient, the different properties of Hall coefficient? Because Hall effect actually describes the behavior of free carriers inside a semiconductor or a material when applying a electric and magnetic field perpendicular to each other to a sample. Hall coefficient actually measuring the Hall coefficient measures the mobilities and electron concentration in the sample. The temperature dependence on Hall coefficient and resistivity will allow us to distinguish between whether the semiconductor is P type or N type. Thus, there are also various applications like it can be developed to electronic device, portable electronic device, and hall sensors. There are various applications to our industry. So we should studying these things is very good. And the theory for the theory we have the Hall effect theory when the charges present in the sample when electric field is applied perpendicular to the magnetic field, then electric field will drift the charge. For positive charge, electric will push the charge towards its directions, and for negative charge, it will pull towards opposite directions of the electric field. And due to the movement of the charge carrier, there will since there is a perpendicular magnetic field present, so it the Lorentz force will cause the charge to accumulate one of the sides. Yes. For we can see that from two images. For the left image, the charge carriers are negative carriers, so Lorentz force will act and accumulate the charge negative charges towards left side of the sample, and the rest of the charges, the positive ion force, will be left with the right side of the sample. So there is a will appear a voltage difference with this distance over the width of the sample, and this voltage difference we call the Hall voltage, and corresponding to the Hall voltage we say the induced electric field, that is the Hall voltage, developed Hall voltage by the distance over which the charges are separated. Hall coefficient defined as the induced electric field re- divided by the current density J is the current density, and the applied magnetic field H. And we can write it like this. So there are actually two types of cases we will consider. The first type of cases when there is only one type of carrier like in a metal, there are whole majority carriers are like electrons. So for one type of carrier we have the expression like putting the Hall voltage and the magnetic field and the current density, that is number density times charge times the drift velocity. We have expression like 1 over number density times the charge of the carriers. So we can see from the expression that for positive charge carrier we have so it will depends on the charges on type of charges. For positive we have one actually for positive carriers we have positive negative Hall coefficient, and for negative charges we have positive Hall coefficient. There is a standard assumption regarding this, and for we can define the mobility of the charge carriers as a number density times charge times mobility is the conductivity of the sample, and from this relation we get the conductivity and mobility and the Hall coefficient relations. So mobility can be measure we can measure the mobility from the Hall coefficient of the sample, and producting with the mm, conductivity of the sample. And when in case of like semiconductors, there are two types of carriers. One is a hole and another is electron. For two types of carriers we have expression for Hall coefficient like this. Now the experimental procedure what we followed to derive those things, and this is the steps. I have described the steps how we measure the experiment. This is our experimental setup, where these are the two poles of the magnets, and there are two coils actually, and the two coils with gives us two magnetic poles, and between the two coils we have magnetic fields. Poles, the current uh, supplied through the poles is the right device supply a current, and that will create the magnetic field. And there is a probe material, the this material, this is the four probe setup. In this material we should present between these two coils. So this is our full experimental setup, and this is the data for calibration curve, and that is the current versus the magnetic field between the two coils. This is the graph we obtain for the calibration, and as expected, it is a straight line passing through our to the origin, passing through the origin. Now we calculate to calculate the dependence of temperature of on dependence on temperature of Hall coefficient. We um, took the sample of germanium p-type sample with medium doping of thickness 0. 0.5 millimeter and the probe current 3.96 milliampere, and we took the data for three types of applied magnetic field, namely 2.2 kilogauss, 2.5 kilogauss, and 2.3 kilogauss. And for three types of data, for all three types, we varying the heater current, we got the corresponding thermo EMF, and measuring the Hall voltage, we get the Hall coefficient. And from the standard list of the thermo EMF versus temperature curve, we got the corresponding temperature for the corresponding thermo EMF for the sample for different heater current. And from this data we plot graph something like this. We got a graph like this, and we see that from the graph Hall coefficient is nearly constant near the temperature around room temperature 20 to 30 degree centigrade. It is almost flat, and after that it decreases gradually, and above 90 degree centigrade it remains almost flat again. This is the for germanium p-type sample we have used. And then we took the data for the determination of a Hall coefficient with the variation of applied magnetic field. We vary the magnetic field for a particular probe current. We calculate the Hall coefficient, and from the data we got the graph plot like that, like this. And in this graph we see that magnetic field, how Hall coefficient changes. It for very low magnetic field, that is we can took almost zero magnetic field, their Hall coefficient is zero. That is no voltage difference between the sample. As we increase the Hall magnetic applied magnetic field, the Lorentz force become much more stronger, and up to the magnetic field 1.23 kilogauss, the magnetic field becomes for that magnetic field, we got the full strength of magnetic field that will accumulate all the charges, three charges present in the sample. And for that those region we got a maximum peak in the Hall coefficient. And after that, when we increase the more magnetic field, then it becomes the Hall coefficient becomes slowly lesser. And from this experiment we can actually see we can actually uh, predict the electron mobilities and electron concentration in the sample, and also the type of semiconductor we have used. This is the reference I have used. This is a book by Puri Baba, Solid State Physics, and the Elementary of Solid State Physics by Srivastava, and the Solid State Physics as from Marmin. And for the experimental setup, we use the PHYWE guideline. Thank you, everyone.